All right, folks, let's get to it. We are going to construct, in this case, a 90% confidence interval for a population proportion or probability P. And what I'm going to do is I'm going to have this Excel spreadsheet on the side so that you can see this sort of algorithmically in this spreadsheet. I'll send this out. And in fact, you could actually use this. Unfortunately, there's no super easy function in Excel that will give us the margin of error cleanly and easily like before when we did confidence intervals for mu, a population mean. But I'll send out the spreadsheet and it will follow the directions, and this will be instructive. So in my Excel spreadsheet, find a 1 minus alpha confidence interval for P where we're using Z critical values. We always will, as long as the assumptions are satisfied. Now, you can use this spreadsheet to check your work, but on your homework, please show work, okay? This is meant to be a check for you. And also, it'll help you out. Hopefully, this will clarify the example. If this makes things more confusing, ignore this. All right. A magician's coin is flipped 500 times. So David gives you a coin, he washes his hands, he gives you the coin, and you're wondering, I wonder if this is a fair coin. I wonder what the probability of heads is on this coin. So you take this coin and you flip it 500 times. So what is 500 in this binomial experiment? 500 is the value of n. It's the number of trials or flips. It's the sample size. So here in red, I indicate what you have to enter. 500 flips, n equals 500. And then these other numbers will change along the way. Now, so 500 is the value of n, is the sample size, the number of trials. Out of the 500 flips, the coin comes up heads 230 times. 230 is a value for x. It's the number of successes we observe, because a head is a success here. See here, we're looking at the probability that the coin comes up heads. So a head will count as success. So this here is the number of successes. It's the number of heads we get in our sample. That's little x. So we're going to enter 230. Little x is 230. All right. We're going to verify, first of all, that normal approximations are appropriate in this problem. I'll indicate this in red. Verify that normal approximations are appropriate. So remember the conditions. We needed NP hat to be at least 5, and we needed NQ hat to be at least 5. And actually, we can do that right now based on these numbers, because it turns out that NP hat is the number of successes. NP hat is X. NP hat turns out to be X. It's 230. It's the number of heads that we get. Okay. And likewise, the number of tails, that's going to be 500 minus 230. Remember, there are 500 flips. 500 minus 230 is 270. 270 is the number of tails or failures, and these are way above 5. These are way above 5, so this checks out. The normal approximations will be appropriate in this problem, and we can proceed. I'll go over these calculations in just a moment, but right now, we can verify that normal approximations are appropriate. The number of successes or heads, in fact, is way above 5. The number of failures or tails is also way above 5. Again, I'll get to these approaches in just a moment. But this does check out, just based on these two numbers, and the fact we have 270 failures or tails. Okay, now this is the long-term thing, find a 90% confidence interval, or CI, for the probability that the coin comes up heads on a flip. We're defining that to be P. I'll put that in purple. So the probability that the coin comes up heads on a flip, we're defining that to be P. It's the success probability, the true success probability. This is a population parameter. P hat here is our point estimate. It's a sample statistic. So again, little p, that is the population parameter of interest. Population parameter of interest. Put this in purple. Okay. And then we'll write the confidence interval in this case with the lower limit and the upper limit. And also we're going to interpret the confidence interval. But that's later on. First off, let's find our key sample statistics here, especially the p-hat. That's really key. But we're also going to need q-hat for later. And eventually the margin of error. And we'll do it to 3 decimal places. Although on homework or exams, I reserve the right to ask for a different number of decimal places. Okay. And eventually, when we get the margin of error, we're going to need these hints from the z-distribution. That's going to help out when we find the margin of error. Or we can use our Excel spreadsheet. All right, let's find p-hat, our point estimate for p. This is our sample success probability. Well, let's use our common sense. So p-hat here. Put this in brownish. P-hat here. That's going to be the point estimate, the sample success probability. It's our point estimate for little p, the true population parameter of interest. It's our sample success probability. Okay, well, use your common sense. What's our best guess for the true probability that this coin comes up heads based on our sample data here, our sample statistics here? Well, the coin came up heads 230 times out of 500. P-hat is going to be x over n. That's a formula. Again, sample size is 500 coin flips. We have x or 230 successes or heads. The sample proportion p-hat is given by x over n. 230 heads out of 500 flips, 0.460. So we get heads 46% of the flips. On 46% of the flips, we got heads out of the 500 flips. Let's go to our Excel spreadsheet here. Okay, well, I've already input the formula. To get p-hat, that's x over n. It's the D4 cell over the D5 cell. It's x over n. I've already entered the formula in. Excel verifies, yes, it's exactly 0.466. It's exactly 46%. Right. And by the way, q-hat, the sample failure proportion or probability, is 1 minus p-hat, is the complement. 1 minus 0.460 is 0.540. So if we got 46% heads in our sample, we got 54% tails in our sample. Okay, and that's verified in our Excel spreadsheet. I put here that the q-hat is going to be 1 minus cell D6. It's the complement. So once you enter these in, these then become automatic in black. All right. Now before, I already verified that the normal approximations would be appropriate because both the number of successes, x, and the number of failures, both the number of heads and the number of tails, were both way above 5. So the normal approximation should be very appropriate even if we don't use continuity corrections. But if you want to use these actual formulas, right, n p-hat, okay, n is 500, p-hat is 0.460, we get back to 230. N q-hat, n is 500, q-hat is 0.540, we get 270. By the way, why is this equal to x? Okay. Well, it's just algebra. Here, p-hat is x over n. If you multiply both sides by n, we get that x equals n times p-hat. And then to get the number of failures, it's n minus x. It's the number of trials minus the number of successes. Right? It's the number of trials or flips minus the number of successes or heads. That's how you get the number of tails or failures. Okay. So if you understand the number of successes and the number of failures, you didn't even need these actual formulas, but you could use these. Okay, so our process is legitimate. Well, we're going to need the margin of error. That's the key thing. And unfortunately, Excel does not have a quick function for that, the way we did for confidence intervals for mu. In fact, there were two. you had confidence.norm if you were using Z, sigma known, and confidence.t in the case where sigma was unknown. So there are two functions. If you wanted the margin of error for a confidence interval for mu, a population mean, but we don't have a shorthand from Excel for a margin of error in this case, a confidence interval for P. So we're going to crank it out. Okay, so the margin of error is, I gave you this. This was the given formula. This was one of the given formulas I gave you up here, right up here. The margin of error is obtained by taking the positive critical value based on the confidence level times the standard deviation for the p-hat distribution. I mentioned the theory behind that, but don't freak out about it. All right, well, remember, we're dealing with a 90% confidence level. We wanted a 90% confidence interval, so we wanted 90% confidence. And you might remember, or many stat students remember, it's going to be 1.645. And that was the hint I gave you. Up here, I reminded you, hey, if you want to find a 90% confidence interval and Z is involved, and we're doing two tails. In our confidence intervals, we're doing two-tailed confidence intervals. In theory, there are one-tailed confidence intervals, but in our class, we'll only do two-tailed confidence intervals. So we have 90% in the middle. All right. It turns out that positive 1.645 and negative 1.645 are the two critical values from the Z distribution that will trap 90% in the middle in such a way that these tails are symmetric in terms of area. So that was from the hint. From the hint, you should get 1.645 here. Now, how can you do this on Excel? It gets kind of complicated. Actually, it turns out that the negative critical value is easier to find. The negative critical value turns out to be easier to find. Okay, so how is Excel going to find this? We're dealing with a Z distribution. We want 90% in the middle, all right? That means we need 10% total in the two tails, right? That's the complement. That's alpha. Alpha is 10% or 0.10. And it's split in halves, right? What's half alpha? What's alpha over 2? Half of 10% or 0.10 is 5% or 0.05. But remember, tables and software like to look to the left. It's actually easier to find this negative critical value than this positive critical value, because this guy right here is going to have 5% or 0.05 to the left. Here's how Excel finds out that the negative critical value is negative 1.645. I'm going to put in the confidence level, 0.90 or just 0.9, all right? And then right off the bat, see, that's the only part you have to enter for this part, because my Excel spreadsheet here knows that alpha is 1 minus that, is the complement, so it's 10% or 0.1. Half of alpha is therefore 5% or 0.05. That's the left tail and also the right tail probability. We're going to focus on this left tail probability being 0.05. And then the negative critical value, using the norm.inv command, okay, it figures out what's the 5th percentile. What's the 5th percentile of the standard normal? So this norm.in command gives a percentile. In this case, of the standard normal with mean 0 and standard dev 1. Okay, and we want 5% or 0.05 to the left. So for the left tail or cumulative probability, it's grabbing the entry from D10. Let's see. Oh, it should be, no, it should be D13. I apologize. It should be D13. This over here, right. Okay, the entry from D13. That's the left tail probability half alpha. So norm.inv, you take the entry from D13, this over here. Again, my spreadsheet already has that. All these entries in black are spit out automatically once you enter the entries in red over here, all right? So you enter the confidence level, 90% or 0.9, use decimal, enter it as a decimal. Then we know alpha is 0.1, half alpha is 0.05. My spreadsheet spits this out. The 5th percentile of the standard normal Z is about negative 1.645. Okay, that's where we get that. In fact, this is even more accurate. But then when we plug into our formula, we're technically plugging in the positive critical value. So I just take the opposite of that. I take the opposite of this entry here. That's the positive critical value. All right. So 1.645 is over here. It's the positive critical value in D17. All right, to get the margin of error, you take the critical value and you multiply by the square root of p hat times q hat over n. Okay, so I already input in there. Okay, it's the critical value, the entry from D17 times the square root SQRT of p hat was in D6, q hat was in D8, divided by n was in D5. So I'm referring to previous cells. It's all in here. All right, and to 3 decimal places, it's going to be about 0.0367 to 3 decimal places, rounding off. Or you could use the idea you want to round up because you want to be conservative. Either way, rounding off or up, 0.0367, right here. That's great to check your work on homework. But on homework, please show me this. At least show me this on your homework. I want to see the work. I want to see what you're plugging in. But this Excel spreadsheet, which again, I will distribute after class, this Excel spreadsheet will come in very handy. If I don't send it out, please remind me. And then to find the limits of the confidence interval, it's same old, same old. For the confidence interval, for P in this case, you take the point estimate. Before it was X bar, now it's P hat, okay, the 0.460. And then you're going to add and also subtract the margin of error, E. Maybe I should put this in brown. Okay, okay, and then the point estimate in purple. Huh? Is that right? I guess I could go either way. All right, I'll put the P hat in purple. Oh, well, how about a different color? How about turquoise? Okay, P hat, that's 0.460. Remember, the coin came up heads 46% of the time, right? 0.460 to 3 decimal places. Give or take the margin of error, which is round off to the same number of decimal places as P hat, 0.037. For the lower limit, you take P hat, the point estimate, you subtract the margin of error, just like before, right? For mu, it was X bar plus or minus E when we were doing confidence intervals for mu. For P, we take P hat and we add or subtract the margin of error. P hat, 0.460. When you subtract E, the 0.037, you get 0.423 to 3 decimal places. The upper limit, 0.460 plus 0.037, that's 0.497. So here's our 90% confidence interval. Remember, the lower limit goes to the left, the upper limit goes to the right. Do not switch these, that's wrong. So our 90% confidence interval for P goes from 0.423 to 0.497. Let's see Excel verify that. Okay, so, whoa, I should have put a minus here.
Welcome to your hearth and home.
Be quiet, Siri. Bye, Siri. Hold on. Bye, Siri. Okay. Hey, Siri. There you go. Siri was bothering us. All right. For the lower limit, it's P hat. Remember, P hat was D6. P hat was in D6 over here. All right. Okay. It's P hat minus the margin of error, which is D19. The upper limit is P hat plus the margin of error. There you go. The lower limit is lower. It's P hat minus the margin of error. It's about 0.423, right? 0.423. The upper limit to 3 decimal places, 0.497. Okay, when you round off. Although again, if you just looked at these and you wanted to be conservative, remember, to be conservative, you can either round up the margin of error and then add and subtract accordingly, or here, subtract and add accordingly. Or if you're just focusing on these entries here, you round out. You round down the lower limit, 0.423. You round up the upper limit, 0.497. So again, to be conservative, either round up the margin of error and do your minus and plus deals, or if you're looking at this, round out. Round down the lower limit, round up the upper limit. But again, don't freak out about that. Rounding off will be fine. So as you see, just by entering in the red entries here, right, once I corrected my signs here, then the black entries are spit out by Excel, right, and here's your confidence interval. So you see, folks, although Excel did not have functions for this stuff, hey, I'm going to send you a spreadsheet, and if you have Excel, if you enter in these red entries, then my nice Excel spreadsheet will spit out what you need. Okay, so I'm kind of doing the functions for Excel. They should pay me. Microsoft should pay me. Come on, Bill Gates. Pay me. All right. Interpretation. Okay, what does this mean? we are 90%, it's a 90% confidence level. We are 90% confident that this interval contains P. But you should say to a layperson what P is. Contains the probability that the coin comes up heads on a flip. We are 90% confident that this interval contains the probability that the coin comes up heads on a flip. So, the coin that David gave us, if he claims it was a fair coin, hey, my friend, this coin is fair. What do we say to David? You're a liar. Or you don't know your own coin. You're either a liar or you don't know your own coin. Because we are 90% confident that this does not contain what value for P. What value for P corresponds to a fair coin? 0.5. That's for a fair coin. But this interval does not contain 0.5. Think about it. What does this suggest about a claim that the coin is fair? If David says, hey, my coin is fair, well, P equals 0.500 for a fair coin. So the fact that this 90% is pretty high, the fact that this 90% confidence interval for P does not contain 0.500, it suggests that the coin is not fair. It's biased. Apparently biased towards tails, actually. Okay, since this is below 0.5. So based on this analysis, and we're going to use this kind of language in the last part of our course, there is sufficient evidence against the claim that the coin is fair. So if David's claiming, hey, my coin is fair, we have sufficient evidence against David's claim based on a 90% confidence level. Although if you work it out, and you can try my Excel spreadsheet for that, in fact, I can do it. It turns out a 95% confidence interval for P would contain 0.5. So under this analysis, there's insufficient evidence. We don't have strong enough evidence. We have a higher and stronger burden of proof to call David a liar. So this might freak you out, and this freaks out pure mathematicians. Different confidence levels may lead us to different conclusions, okay? I mean, if we had a 100% confidence interval, that interval goes from 0 to 1. Well, yeah, of course P is going to be somewhere in there, right? I mean, we're 100% confident P would be between 0 and 1, but then that doesn't give us any information. We have no basis to call David a liar, right? I mean, if our confidence interval is 100% and it's going from 0 to 1, well, there's no way that I mean, it's going from 0 to 1. There's no way that we're going to call David a liar. Okay, because 0.5 is obviously going to be in an interval between 0 and 1. For a 100% confidence interval, I know the interval is going to be between 0 and 1. I know it's going to contain 0.5 for sure. Okay, so yeah, different confidence levels probably will lead you to different conclusions, right? Based on 90% confidence, we have sufficient evidence against the claim to call David a liar, right? But under 95% confidence, okay, that's not enough evidence. We wouldn't have enough evidence. Take a look here. Here's how my Excel spreadsheet would show that. Okay, so I'm going to go over here. I'm going to enter 0.95. Boom. Here's alpha. Here's half alpha, right? Negative 1.96. Sound familiar, right? That's the negative critical value. 95% for Z. Here's his positive partner. Margin of error will be about 0.044. Okay. Confidence interval from 0.416 to 0.504. Does this confidence interval contain 0.500? Yes, it does. So we're not ready to call David a liar for a 95% confidence interval. Okay. What if we did 100% confidence? I was not even going to try. What if we did like 0.99999? Pretty wide. 35% to 57%. I'm surprised it's not even wider, but yeah. All right. Anyway, that's our key example with some interpretations and kind of theorizing. Next up, what sample size do you need in order to get a confidence interval of a certain margin of error, certain half width? Next time.